Hello again, everybody, and welcome back. This chapter on potential energy in springs, so far we've been talking about gravity as being the main creator of a conservative force. It does conservative work. That's certainly true, but what's also true is that springs do conservative work, or that is, they create conservative forces. If you cause a spring to do negative work, that is, if you displace a spring and compress it, it'll be now prepared to do positive work so that it returns to its original position. And you may recall Hooke's law from the former chapter. We said that Hooke's law is the force created by a spring equals kx. All right? That is the spring constant. K is the spring constant. It's measured in newtons per meter. And if you compress or elongate a spring by a certain number of meters, it will feed back with a certain number of newtons of force, proportional to how much you displace that spring. So therefore, if we take force times distance, that is, force from a spring equals kx, times a distance x that you displace the spring, it'll produce an angled slope. That is, if you don't displace the spring at all, if x is 0, then your force is going to be 0. But if you displace it some distance, it's going to feed back with a force proportional to that. And if you displace it twice the distance, it's going to feed back with twice that force right there. So you're going to have a linear relationship between the spring, so that is the force that the spring creates, and the amount of displacement that the spring undergoes. But if we're talking about work, the most basic definition of work is force times distance. All right, and that's easy to calculate graphically right here if you've got a constant force, but with a spring you've got a variable force, because the more you displace it, the more force the spring feeds back. So really what we need to do is find the area of not a square or rectangle, but the area of a triangle. The work of a spring right here is going to be represented by this shaded area that I'm shading in. So how do you find the area of a triangle? Well, that's 1/2 base times height. And that's what our definition of the work done by a spring is right here. Here's our 1/2. All right. The height is your kx, and then multiplied by the base x, that's where the squared comes from, right there. So 1/2 kx squared is really the area of this triangle, which is the definition of the work done by a spring. All right. So springs do conservative work. The conservative work done by a spring is described as 1/2 kx squared. It's the negative of the change in potential energy. So if you have some potential energy in the spring and then no potential energy in the spring when it's finally done being releasing right there, that change in conservative work that the spring has done is really going to be described as our 1/2 kx squared. So while a spring is all coiled up, or you might say compressed, you could say that the potential energy in the spring is 1/2 kx squared as well. Now, in a previous problem, I did US, that is our potential energy U, sub S, as I think we did a problem earlier on as the potential energy in a Snickers bar, right? And I may have indicated US as the potential energy in a Snickers bar. But going forward from this point on, U sub S, the potential energy is going to be is going to refer to the potential energy in a spring. All right, so U sub S right here. So however much you displace a spring, and knowing its spring constant, 1/2 that k times x squared, is going to tell you the amount of potential energy, or the ability to do work that is now present in that spring. So let's see if we can do an example that relates kind of Hooke's law, that is force of a spring equals kx, to our understanding that the potential energy in a spring equals 1/2 k. That's not a k, it's an x. 1/2 kx squared. And that's going to be in this example 8.5. So we are told that if you take a certain spring and you displace it a distance of 2.25 centimeters, or let me put it this way, if you apply a constant force to it of 120 newtons, all right, the force equals 120 newtons. it will cause this spring to displace to the tune of 2.25 centimeters. All right, so our x right here is 2.25 centimeters. Now let's convert that right off the bat to meters. So we're going to move that decimal point over to the left 2 places, right? So 0.025, oh no, I'm sorry, 225 meters. All right, and the reason we're told this is because we're asked later on, what is the potential energy in the spring when you compress it 3.5 centimeters? All right, well, we just learned that the potential energy in the spring is 1/2 kx squared, but what we don't know is the k. We don't know the spring constant, the k constant. But we can use our force and our displacement up here to find the spring constant. Because since Hooke's law tells us that the force in a spring equals kx, then we can say that the k is going to be the force in a spring divided by x. The amount of force that you apply to the spring, 120 newtons, is going to be the amount of force that the spring is pulling back on you, right there. So that's going to be equal to negative F1. And so we can find out the spring constant of the spring simply by dividing the force, that's 120 newtons, divided by 0.0225, sorry about that, meters. And so our spring constant, our K constant, should be this. I get 5,333 newtons per meter. Okay, that's you might say the stiffness of the spring, or the springiness of the spring. Let's put a dotted line around that. That, of course, is not our final answer. But we can use it to get our final answer, because we've been asked what is the potential energy in that spring if we now compress it a different distance. So our x now is, we'll call it x2, is going to be 3.5 centimeters, and that is that's not a 0, it's a 3. 0.0350 meters. And we know the spring constant because we just solved for it. That K equals 5,333, nope, too many threes, newtons per meter. Let's find out what that comes out to in terms of joules. That is potential energy joules locked up in that spring right there. So that's going to be 1/2 K. So the K is 5,333 times our x squared. So that's 0.035, that value squared right there. That's going to give us the amount of potential energy locked up in that spring, times 0.035 squared. I get 3.27 joules. So 0.5 times 5,333 times 0.035 squared, that's what I get. 3.27, it looks like an S, that should be a J. Potential energy in the spring is 5,327 joules. And that's our answer. So we can keep in mind Hooke's law. That is, Hooke's law is the force that is applied to a spring is going to result in a certain displacement in the spring given the spring constant. And of course, knowing that relationship allowed us to solve for the spring constant, which we can then put into our description of the potential energy in a spring. So if we know the displacement, and again, the displacement can be positive or it can be negative, it doesn't matter. It's going to be the same feedback of force from the spring. We take that 1/2 kx squared, and we have our potential energy in our spring. So above this line right here was the first part, and below it is the second part. But we can use those two understandings, Hooke's law versus potential energy in a spring, to solve this problem. All right. Well, that's it for this segment right here on potential energy in springs. Thanks for following along. Just make sure if you have any questions that you come see me, and I'll try to help you out. Thanks a lot. I'll see you on the next one.